Welcome to Confidence Intervals Part 2. To recap, in Season 1, or Part 1, we learned, hey, what happens when you know the population standard deviation? How do you calculate the confidence interval for the mean? We had a formula. Now, the exciting conclusion of confidence intervals. What happens if you don't know the population variance? It's known, it's hidden from you. Now, how do you unravel it? How do you calculate a confidence interval for the mean? Not so hard. We just use a t-distribution. Before we used the z-distribution, now we just do a t-distribution. When we're faced with calculating a confidence interval for the mean, we ask ourselves one question. What would Alan do? Well, no, we ask ourselves a different question. Is sigma, the population standard deviation, known? Simple question. If the answer is yes, we use the confidence interval we learned in Part 1 based on the z-distribution. If the answer is no, we use confidence interval formula based on the t-distribution. It looked pretty much the same, except now it's based on the t-distribution, and we estimate sigma using the sample standard deviation. With t-distribution, there is another piece of information we need to keep track of, is the degrees of freedom, n-1. So degrees of freedom the z-distribution doesn't have any degrees of freedom, but the t-distribution does. And many other distributions that we'll talk about throughout this course will also have degrees of freedom as one of their parameters. So we go on, and we have the formula. I wrote it down in my messy handwriting, but we also have it in nice, clean handwriting. So it's just basically a binary world. If I know the population standard deviation, do this. If I don't know it, do that. Okay. The interpretations stay all the same. Everything they're used the same. They're just calculated a little bit differently. Okay. The t-distribution is what you'll face most of the time, because typically we don't know the population standard deviation, right? And the t-distribution is the normal. It's both are bell-shaped, both are symmetric. They look very much the same, and in fact, once those degrees of freedom get to be sufficiently large, they become exactly the same. So as we saw from that graph, both are centered around 0, right? The standard normal and the t-distribution both center around 0. However, the variance for t-distribution is larger than 1. And we remember from our Part 1 experience, the variance and population standard deviation for z-distribution is 1. So, because we get those fatter tails. As the degrees of freedom get larger and larger with the t-distribution starts to get closer and closer to the z-distribution. And theoretically, once the degrees of freedom are infinity, the z and the t are exactly the same. Now, they start to look very, 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 very similar before then, but the t starts to converge into the normal z-distribution as we have a larger and larger sample size, essentially. Which makes sense, right? As we have more information about the population, we start to approach the size of the population, and one would expect that at that point we've got all the information from the population, just like we would have for a z-distribution. All right, so let's go back and just do this question again. So we saw this question as example 1 when we assumed that we had the population standard deviation. An unrealistic assumption, granted, because how could we know what the population standard deviation would be for all employees, right? Hence the population. More realistically, we take a sample. Based on that sample, we try to estimate the population standard deviation, but really what we're in essence working with in the real world is the sample standard deviation. Okay, and a common question is, how do I determine? It says standard deviation. Is it population? Is it sample? Blah blah blah. I mean, how do I know? If the words aren't explicit, it's a sample standard deviation. Okay, so if it just says standard deviation, assume it's a sample standard deviation, because that is the more likely event, is we just simply don't have all that population information available to us. So sample standard deviation, just the word standard deviation, we can assume that they're interchangeable. If it says the words explicitly, population standard deviation, then you can assume that you know the population standard deviation. But if you don't see that word population, or you don't see the Greek letter sigma, you don't know the population standard deviation or the population variance. Okay. So just to reiterate that again, you can speed through the next 10 seconds if you like. If you are not explicitly given population standard deviation is, you don't know it. Or if it doesn't say sigma is, you don't know it. Okay? And therefore, the standard deviation that you see in the question is going to be the sample standard deviation. Okay, so we have our example number 2. Okay? And based on the information from before, which I'll recap, we had an X bar of 40,000. We had, and now we're assuming that the standard deviation is a sample standard deviation, 40% of that 40,000, which is 16,000. Okay. We have a sample size in the previous example. We assumed it was 36. We'll keep that 36 for this one. And now we'll calculate a 90% confidence interval. So we want a 90% confidence interval. Okay. That means the alpha is 0.10 or 10%. Alpha over 2 is 0.05%. 10% divided by 2. Nothing too terribly crazy so far. Okay. Now, we have a couple of different ways that we can do this, and I'll do it one way with the tables just in case you don't always have Excel really handy, but we'll also use Excel to calculate this as well. Okay, so we have our tables, and this is a typical kind of way you see the table. Sometimes, as we saw with the standard normal, sometimes you're getting the areas to the left of the areas to the left of the z-score. Sometimes you're getting the areas to the right of the z-score, and you had to be very careful about reading the tables. T-distributions are almost exclusively used for confidence intervals and hypothesis testing. Right? So everything is sort of designed or set out with that in mind, which means you're always getting areas to the right. I've never seen an area to the left t-table. It's goofy. It makes no sense to do it that way. So we have our n is 36, which means our degrees of freedom is 36 minus 1, n minus 1, which is 35. So now we're all set to look up our t-stat. So our journey always starts with the degrees of freedom. So degrees of freedom is 35. So I go along that row of 35. Okay, cool. And I have my alpha over 2 of 0.05. And so I keep going until I hit the 0.05. And my t-score, or my t-alpha over 2 in this case, is 1.69. Okay. So we have the 1.69 there. That comes out of the tables. Alternatively, we could have looked at it and said, okay, I'll bring Excel in here. And I have a function, and the function is listed in the last one of the last slides, but we can go equals to t. Now, a bunch of choices come up. Now, we like the norm inv, right, when we were trying to find z values. T-inv does the same for us here too. I'll scroll down to the modern t-inv because, of course, it's more complicated looking, but t-inv.2t, two tails, right? Confidence interval is two tails. In theory, we could find a one-tailed version of this as well. Okay? So t-inv, two tails, and we see probability. All that probability means what's your alpha. Excel will do the divide by 2 in behind the scenes, so 0.10 is our alpha. In the lab, they'll show you how to do it in more neater, where you set it out and everything. I'm just using this as strictly calculation table lookup kind of stuff. Okay, so there we go, right? There's our alpha, there's our degrees of freedom. Same kind of things we use to find the value on the table, right? I push enter, I get, it's 1.6895. Okay, so close to 1.69, right? Rounded at the 3 decimal spots, we'd have got 1.69 in both cases, right? So same value, your choice as to which one you use, depending on the restrictions on the exam and so on. Okay. So now we're able to continue on with our quest here and bring everything together and find the actual confidence interval. So we're going to first find that margin of error, ME, margin of error, and we have the T, alpha over 2 of 1.69, the S of 16,000, right, and the N of 36. Right. And I get my margin of error to be $4,506 and roughly 67 cents. Again, the rounding is pretty loosey-goosey in stats as a practical matter, because look, we have a sample standard deviation of $16,000. Whether we go to 2 decimal spots and get it to the penny, whether we go to 1 decimal spot and get it to the dime, going to 4 decimal spots just becomes a little bit odd or a little bit weird, because you have what's called precision without any accuracy. So now we're able to find our upper bound and our lower bound. So our upper limit will be our mean, 40,000, plus the margin of error, right? Just following our formula. And we get, what do we get? $44,506.67. Okay. Lower limit, same kind of idea. So now we go 40,000 minus the margin of error. So minus $4,506.67. And that one gets $35,493.33. Interpretations are exactly the same. Hey, if you have a postulated value, could it be 42,000? Could the mean be 42,000? Yes, it could be. Why? Because it's in the confidence interval, right? So we have a little bit of obtuse language in that, like we talked about in part 1. We lack any evidence to suggest that 42,000 is not the population mean. It's a little unsatisfying, but there's some technical reasons for that, centered around not wanting to accept HO, which we'll talk about in the hypothesis tested unit. However, if somebody was to come out to you and say, hey, could it be 35,000? We go, hey, 35,000 is not in the confidence interval, therefore in this case we're 90% confident that 35,000 is not the population mean, right? And that's all centered around the fact that 35,000 does not fall in this particular confidence interval. Okay, so very useful, very easy to calculate, very powerful, simple and powerful, just a dynamite combination. Okay, now when from a practical matter, if you don't have Excel handy, which sometimes can happen depending on your exam situation mostly. If the degrees of freedom is not on the tables, typically you could pick the closest one. That's justifiable. All things equal, the smaller one is the more conservative bet. So it's kind of like the err on the side of safety or caution to pick the smaller degree of freedom. And if it gets to be really, really, really big, like it's bigger than any degrees of freedom on your table, then you can make a pretty reasonable argument for just using the Z distribution to approximate the T. Okay, if you look at the tables, often I didn't copy it here, but often at the bottom, the sort of the last item on the table might be under degrees of freedom a little letter Z or an infinity symbol, and that just means they mean the same thing in this case. If it says a little under degrees of freedom says Z, it means, hey, this is the Z distribution values. If it says infinity, under the degrees of freedom, it means, hey, those are the Z values across that particular row. So you can just use the largest row. So let's say we have 79 here, and we had that little infinity symbol as the last one. we had 482 degrees of freedom, then we could justify and just use the Z distribution. You'll notice that the numbers aren't really getting that far apart anyway. I mean, you look at how far apart are these numbers, right? 1.992, right? Not 991, 991. I mean, they're not, as the degrees of freedom get to be higher and higher, there's not much difference between them anyway, so it's kind of not worth getting too, stressed out about. Okay, let's do another example. Now, current trends in job search strategies of BCom graduates are studied in an annual survey. In a recent year, the average number of applicants submitted to organizations by a random sample of 16 participants. So let's get that down. 16 is our sample. Was 12.82, so that's our average. X bar is 12.82 with a standard deviation of 3, again, assuming that's sample standard deviation because it does not explicitly say there. Population standard deviation doesn't explicitly say sigma, so we're going to assume that it's S. Give confidence interval estimates for the true average number of applicants submitted. It's at this point that I would suggest you do two things. First thing is look up in the tables the proper T distributions for a 90% confidence interval and maybe a 95% confidence interval and so on. And if you want, sometimes a 99% confidence interval is not too bad as well. So those are sort of like the three popular confidence intervals. Secondly, I would suggest that you pull in your old Excel and say, hey, calculate that up and just check to make sure that there's an agreement. Excel, as you can kind of see when we were doing it, I think it's the faster choice if that option is open to you, but it really is your call. Okay. So we have our tables. We look it up. Our degrees of freedom, n minus 1. So 16 minus 1 is 15. So our journey will start in the row with 15. And we can kind of see a 90% confidence interval, a T alpha over 2. And the 90% case would be 1.753. The T alpha over 2 in the 95% confidence interval case, again, that would be where each tail has 0.025. Remember, alpha over 2. If alpha is 5, alpha over 2 is 2.5 or 0.025. So 2.131 and that kind of idea. Okay. Again, we can always punch this into our calculation here, right? And all we're essentially doing is just changing the amount of information. 15. And we see 1.753. We had 1.753, right? We can then change that to alpha 0.05 for a 95% confidence interval. And we see 2.131, a couple extra decimal spots there versus the table, but they're very, very, very close. Nothing bad will happen regardless of which one of those two versions you pick. And here's a whole bunch more if you want to practice 98% and you want to practice 99%, which I encourage you to do. And just to see that you can confirm that you can calculate this, okay? Recommend now you finish off the problem. You can kind of see that for a 90% confidence interval, I've done it all but the end math here. So here's sort of where you should end up. But you want to be able to, you want to go through every one of these questions and duplicate that you're able to do it. Nobody cares whether I'm able to do it or not. Okay. All right. Okay, one last kind of set of questions, just mostly for fun. This is off of information, win percentages as of January the 3rd, 2020. before everything went all nutso. So, obviously right now there's no hockey, and when I'm doing this is January the 2nd, 2021. But we have some data. It's kind of fun data. This is all based off of when Las Vegas first entered the league. There was this talk about the Vegas flu. That visiting teams, they go to Vegas, and before COVID there was all sorts of distractions, and they kind of come to the game maybe in not the proper mindset. I remember, I think Connor McDavid had his 21st birthday in Vegas, so I can't remember if Edmonton won or lost on that one. But there's sort of this, fun thing, hey, can you go to Vegas? Is there an advantage to the Golden Knights being in, sort of somewhat immune to the lure of Vegas, but yet all the visiting teams with all their young men with lots of money, maybe not so much. And so I looked at the home versus away record, right? Because you want to make an adjustment for the fact that sometimes teams are better than other teams, right? And up to this point, and Vegas had a pretty good run in the playoffs as well. Vegas was good at home and they were good away too. And so you want to make that adjustment for that differential. Are they that much better at home versus being out on the road? And then I thought I'd throw in Winnipeg, because Winnipeg had I think Winnipeg was playing playoffs, I think, with San Jose. This is like a year or two before 2020. I can't remember if it's 2018, 2019. COVID kind of messes up your timelines, right? And one San Jose player was whining and crying about there's nothing to do in Winnipeg. I just can't really get into playing. I just don't feel it. I just don't feel motivated. Whine, right? Guy gets paid millions of dollars is whining about whether there's enough fun stuff to do in Winnipeg. But anyway, so I thought, yeah, hey, let's throw Winnipeg in there. And so we see some interesting results. We do see Vegas, look at that. Almost 1.5, right? In 2019, now it was 1.15, so maybe the Vegas effect is becoming less so. So that was pretty interesting, because in 2019 that was massive. And Winnipeg, however, Winnipeg doesn't even like playing in Winnipeg, right? So you can kind of look and you say, look, Winnipeg's away record is way better than their home record. Like, what's that all about? And so that's kind of funny. In Edmonton, they don't care. It's the curse of Rogers Place, I think. I think it's haunted or something like that. Edmonton kind of goes, hey, yeah, I know. Hey, really like that $600 million arena. Do we play better in there? Nah, not really. So money well spent? I don't know. Maybe that's too controversial. Okay, so run through the numbers, and so we run through do all that for all the teams, right? So for 31 teams, and we see our results. So let's find a confidence interval for this case, and let's do it for a 95% confidence interval. And so we have our mean, which is, so here on the output it doesn't say sample mean, but it's assumed to be sample mean. 1.22. Okay, so the typical ratio is 1.22. We kind of say, hey, Vegas is a little bit was much higher than that, and it's kind of not so much anymore, right? We have S, which is the sample standard deviation, or just standard deviation in this case. I'll just abbreviate that to 0.45. And then lastly, we have our sample size, 31 teams. Which means our degrees of freedom is going to be 30, right? N minus 1. So alpha with a 95% confidence interval, alpha will be 0.05, alpha over 2, 0.025. T alpha over 2, and now we can look that up. Now let's just bring let's bring the Excel back into the box here. And we'll go with 0.05, and degrees of freedom is 30. Okay, remember with the command t.inv.2t, Excel automatically does a divides by 2 in the background, so we don't want to be dividing by 2 twice, okay? So I just leave it alpha as alpha. And so I get to 2.042. Okay? And you can look it up in the tables, and you'll get the same number. Okay. Let's get that out of the way. So now we are able to bring this all together, just like we did before. We have our upper limit of 1.22 plus 2.042 times by standard deviation of 0.45 divided by square root of 31, and the lower limit 1.22, again minus that same value, okay, which is 165. So we have an upper limit of 1.389. We have a lower limit of 1.059. So we see that there is definitely a home ice advantage, and that seems pretty apparent with the fact that in our 95% confidence interval is completely above 1. 1 would mean you don't care whether you play at home or you play on the road, just like Edmonton. But here it appears that there is a preference for playing at home versus playing on the road. So when we look at the Vegas numbers, kind of interesting, right? 1.15, that falls in that interval. The Vegas flu is gone. It's been vaccinated. Right? 2019, that Vegas flu was raging. Right? Now, not so much. Winnipeg, there is a Winnipeg flu for sure. Right? And even a little bit of an Edmonton flu. Edmonton in that away teams, it's a negative flu in a way. Winnipegers, the Winnipeg Jets don't like to play in Winnipeg. Home teams come in, they do fine in Winnipeg. Right? There's no depression in the peg except for the Jets. There's no depression in Edmonton except for the Oilers. So it's kind of ironic in that particular instance. Okay? So kind of interesting results there. And we can use confidence intervals to kind of see, hey, how strong is that home ice advantage, and do certain teams have a home ice advantage or not? Right? So it's kind of cool. And here's all the commands again on that very last slide to sort of sum it up so that you don't have to remember too much. But this is a very nice slide, and when you go to do it, the stuff in the lab, nice slide to keep track of, because the lab instructors will do a great job of showing you how to do all the Excel commands. But sometimes you forget, you forget that .2t, and odd things can happen as a result. Okay, if you have any questions, always feel free to ask. Thank you.